Yes. Of course. I start when you say.
Okay. Good morning, everyone. On behalf of the organizing committee, I'd like to welcome you to the Winter School of Complex Systems. And as you know, there is an outbreak of coronavirus in China, so which makes the international travel a little trickier. So we have updated our meeting agenda. You can get a copy outside in the registration desk. Being said that if you're not feeling well today, we encourage you to go home and take a rest. You can join us online through the live streaming, live broadcasting. Okay, so this year in the winter school, we focus on two subjects. One is the population dynamics and evolution in ecosystems, which is organized by Dr. Shihong Yan from Academia Sinica. And the other subject is stochastic thermodynamics, and it is organized by Professor Zhang Zhenghong from National Zhonghong University. So a special thanks to Dr. Shihong Yan and Professor Zhang Zhenghong. It wouldn't have been possible without their efforts in organizing this winter school. So thank them very much. So without further ado, I will just give my time back to Hong Yan.
Thank you very much. Thank you for coming. Welcome to our winter school. I'm Hsinchu from Academia Sinica. I'm one of the organizers. And before we start, I want to remind you that this is a winter school. So the purpose of the school is to learn. And one important part of learning is to ask questions. So I invite all of you and ask questions. And personally, I always feel I learn more when I ask questions. So please join the meeting and listen actively to our talks. And feel free to interrupt and ask questions when you don't understand. Especially we have quite different interdisciplinary topics this year. So our first speaker is Simone Pigolotti from Okinawa Institute of Science and Technology. Simone is from Italy. His background is statistical physics. He was studying and working in many famous institutes such as the CISA, Niels Bohr Institute, and Max Planck Institute. He was done many interesting works on biology, ecology, population dynamics, and stochastic thermodynamics. I met Simone 2 years ago in another winter school in France, where he gave a very nice, insightful, and clear talk. So it's our pleasure to have Simone as our very first speakers in our winter school. I really appreciate Simone making the effort to teach at our winter school. and make a nice international connection. But however, unfortunately, because of the coronavirus event, it's not ideal for Simone to come personally. So he is going to present the internet. Here it is. And so please join me in welcoming him. Thank you.
Thanks a lot, Peng Yang, for the very nice introduction. I hope you can hear me well. I would really have enjoyed being there with you, especially because the two topics of this winter school seem to be quite different between them, but they're actually two of my most favorite research topics. But yeah, so I'll be happy, despite the fact that this presentation is remote. You will, feel free to ask questions. I hope the connection will permit to make this interactive as possible. So the common theme of my tutorial and the talk this afternoon is the role of space in ecology and the relation between ecological models and non-equilibrium statistical physics. So I'll give you a bit overview of the things I will tell you about. Well, this morning I will briefly talk about stochastic competition between ecological species. I talk about in particular one of the simplest class of models, which are neutral models that allow to predict patterns of biodiversity in ecological systems. And in the last part of the tutorial, I will focus on the idea of spatial competition and scaling properties of ecosystems. And again, here I will mostly emphasize the connection between ecology and statistical physics. Most of the material in my tutorial is based on this review article that we wrote on the Journal of Statistical Physics in 2018 that I've provided as a complementary material for my tutorial. It's actually one of the first ecology papers that I write for a physics journal, so it has been a way of somehow summarizing ideas about scaling and criticality that we explored during the years, but we ended up mostly publishing in biology journals, so we didn't include all the technical details that are perhaps more interesting for statistical physics. And in my seminar this afternoon, I will essentially present two different papers. Both of them are related with the stochastic competition space. So the first, both of them are related to the other idea that I will introduce, which is bet hedging. And bet hedging is the idea that the same population can include individuals that adopt different phenotypes, and these phenotypes correspond to essentially different evolutionary strategy. So by diversifying its strategy, a population can maximize its survival chance. And so I will discuss two examples. So one is a concrete biological example, which are jellyfish, and I will talk about their life cycles. And later in the talk, I will present this most recent result from my group, which are related to, in general, what happens to an expanding population that expands as a wave, when inside the population there are different strategies and the population can diversify. So let me come to the main topic, which is competition and neutrality. And to introduce this, I want to show, before talking about natural ecosystem, I want to show you this very nice experiment in the group of David Nelson in Harvard, a bit more than 10 years ago now. So what you see in the photo is a growing colony of E. coli, and there are in this picture two different strains that you can see with two different colors, and these two strains have been labeled by two different fluorescent proteins, which have again two different colors. So there is biological engineering in creating these strains, but the interesting thing is that these two colors are different by only one mutation. So these the genome of these two species are identical except one base pair. So they are essentially the same species, they are just of different colors. They are as close as it is possible in biology. And the experiment was as follows, so that these two species are inoculated at the center of the plate. So what you see is a photo of this plate from above, and then they grow radially. So you have an initial colony that spreads radially and becomes larger and larger on the plate. And what you can see is that in the beginning the two colors are blurred, but then after a while these two species start forming domains. So you have green sectors and red sectors. And this is because when individuals start reproducing and spreading in space, their progeny has the same color as their mother. And so even if they were mixed in the beginning, they tend to separate in time. And you can see that so the lines are the boundaries between these two species, and so there is competition between them, but since these two species are basically identical, no species is invading the other on average, but the border between these two domains seems to do some kind of random walk. So this is the idea of neutral competition, so you have two species, but you don't have the classical situation in which one is fitter than the other. They are basically identical, and the outcome of competition is just determined by fluctuations. So there has been a lot of debate about how common is this scenario in nature, and this debate is basically unsolved, so there is still people arguing about this point. But we will take these neutral models somehow as the simplest representative of ecological models, and we will use them to explore some of the scaling properties that you would expect in competing ecosystems. So most of the ideas about neutral theory applied. Is there a question?
Yes, a quick question. So can you go back to the previous slide, please?
Yes.
So is this pattern dynamic or static? Like, is it when it goes to a static pattern in the end? Or will this pattern keep changing? The boundary will keep changing when the vibration hits the carrier?
Yeah. So this is a good question. So it's imagine that there is an initial inoculation, which is what you see it mixed, and then this will grow a few millimeters per hour, and at some point the pattern is frozen. So you would have growth at the since it's on a rigid plate, they won't move. You see what I mean?
Right. Yeah.
So you can think of the radial direction as time. So once they expanded, the pattern remains frozen. It doesn't evolve anymore. But this, of course, depends. So you can have a more liquid plate where individuals can move, and then the pattern would be different. Does that answer your question?
Yes. Yeah. Thank you.
Okay. So so the idea of applying these neutral models to ecosystem was mostly due, or at least popularized by this book by Stephen Haber in 2001. And this has been a very influential but also very controversial book in ecology. And in the next few slides, I'll tell you a bit how these models go. So first of all, let me introduce you the simplest neutral model for biodiversity that you can think of. So in this model, essentially, we have a bunch of species. Each species has the same birth rate and death rate. And the death rate is slightly higher than the birth rate, so the species eventually will go extinct. But then extinct species are reintroduced into the system with a small rate. So if you do the math, you can write a master equation for the probability of a species among those that are existing to have a population size equal n. And so, since all individuals reproduce independently, if there are n individuals, the total birth rate will be the individual birth rate times n. And so you can write a simpler birth death process like the one I showed in the slide. And you can ask what's the stationary distribution of this process. So you can solve this equation by imposing detail balance. So basically, assuming that the birth and death will balance each other, so this would be this equilibrium condition that I put here, and this permits to compute the stationary distribution, and you would find that P of n is the case like 1 over n with an exponential cutoff, which is essentially determined by this ratio B over D. So if the birth rate is very close to the death rate, this ratio is close to 1, and essentially would have this yeah, power law decay of the population, the expected population size with this cutoff at the end. So this is a very simple.
Question, please.
Yes.
Please say again what is Pn of t?
Say it again.
Can you please say again what is Pn of t? What is Pn? What the probability of what?
Pn is the probability that a species is made up of n individuals at a time t. But then we assume that there is some kind of steady state, so this probability does not, eventually will not depend on time.
Right, thank you.
Okay?
Yeah, thank you.
So this, if you plot this solution, you can see that actually, despite it's a simple model, it can reproduce quite well distribution of some number of species having a given number of individuals in some groups of organisms. For example, this is a data set of moths. I believe they have been collected in England, and the line is the distribution that I just showed you. And you can see the histogram, for being a simple model, it's actually not so bad. So essentially, in a nutshell, Hubble's theory is a slight generalization of this model, in which you're saying that there is a big population, which would be the mainland, which evolves according to the process I just described. And then this is coupled to islands, which are local ecosystems. And individuals can immigrate and emigrate in and out of these islands. And really the model is adapted from pre-existing models in population genetics, and there is really a correspondence. So the unit in population genetics are genes or alleles, whereas in community ecology would be individuals. And the source of diversity would be mutations in population genetics and speciation in ecology. But really, mathematically, these models are actually rather similar, and the mathematical progress that is made in one field can be easily exported in the other. So this more general neutral model, which includes immigration and immigration, will predict a distribution which has a peak, is not decaying like the distribution we just computed. And this also can be shown to be a rather good description of a relatively limited ecosystem. So if you sample, for example, trees in a forest, you get this kind of distribution. So these are all different tropical forests all around the world. And the line, I hope it can be seen, unfortunately the line is a bit thin, is the prediction of Hubble's model. So it's a quite simple model, but it's quite appealing for physics because lots of these models can be solved analytically, and they can be compared with this distribution and make quite quantitative predictions. So the classical state case studies have been tropical forests because first they're interesting for conservation ecology, and also because it's easy to count trees because they don't move. But recently there has been a lot of interest in thinking about applying these ideas to microbial communities that can be accessed by other means, for example, metagenomics. And important examples are bacteria communities in microbiome inside organisms, or also planktonic communities. So the real main theme of my talk will be generalization of these ideas to understanding biodiversity in space. So if we think about a big ecosystem, again, I keep thinking about the tropical forest as the classic example, and the queen of tropical forest perhaps is Amazonia. So you can think that the ecological patterns you would see in a system like this would vary across spatial scales. So the Amazonia is a huge forest. It covers almost 10 to the 7 square kilometers. And you can imagine of taking this satellite picture and zooming in and looking at patterns as you vary the spatial scale at which you observe this system. So this idea is not new and has been applied in ecology for a while. And the simplest thing you could do is to simply count how many species you find on average when sampling an area of a given size. So if you do this thing for tropical forest, you will find that the expected number of species as a function of the sample area grows like a power law, and the exponent is less than 1. So this is what you see in this plot that I show here, and these again, the points of different types are different tropical forests. And you can see that there is a rather clear power law behavior spanning over maybe almost 6 or 7 orders of magnitude. And all tropical forests seem to fall on this general pattern. So this picture is taken from this paper by Lonsdale. I added myself another forest in Europe, which is the Black Forest, which has an area of a bit more than 10 to the 4 square kilometers, and it has about 8 different species. So clearly falls outside this pattern. And the reason why I did that is just to give you a sense of what universality would mean in ecology. So you see this kind of scaling pattern that is reminiscent of scaling in statistical physics. At the same time, this pattern contains some information about what the ecosystem is about, because if I try to add to this pattern a forest that is not a tropical forest but is a continental forest, it clearly would have a different behavior. It would not fall under this law. So there is some kind of general scaling pattern, but again, it's partially determined by the features of the ecosystem itself. So more in general, what people observed for other species that can span an even broader range of scales is that often these so-called species area curves, so again the expected number of species as a function of the area, tend to have these 3 different shapes. So if you sample very small areas, the number of species increase very quickly. Then the increase becomes much more shallow, so it would be sublinear, so with an exponent much smaller than 1. And then it would go steep again when you reach very large scales. And the range of exponents in the middle regime, which is often considered the most interesting one, is quite different. So it can vary from something like 0.3, 0.4 to very, very shallow exponents, something like 0.1 or even less. And it seems like microorganisms, for example, tend to have very shallow scaling growths, whereas bigger organisms like trees tend to have a steeper species area laws. So to try to understand this pattern, I will introduce the simplest possible spatial model, which is again a neutral model, just to keep things simple. And this model is related to the so-called Botter model in statistical physics. And the idea of the model goes as follows. So you have a lattice, which is, for simplicity, a square lattice, which contains an arbitrary number of species, which are here represented by different colors. So at each time step, one individual on the lattice will be chosen at random, and with a probability 1 minus nu, where nu is the only parameter of the model, this individual will be killed and replaced by a copy of one of the neighbors. So this will be a death and birth event. So we assume that the ecosystem is saturated, so there are never empty spots. So as soon as an individual dies, it will be replaced by one of the neighbors. So this assumption would be realistic for an ecosystem like a tropical forest, where there are lots of resources, and every time there is a gap, it will be filled immediately by another tree. And there is, since species can go extinct and will lie some kind of non-trivial balance, with a small probability nu, instead of copying an individual with the same species of one of the neighbors, we would replace the gap with a new species. So this is what you see on the left of the slide. Is that clear? So there is only one parameter in the model, and at some point a steady state would establish. And what we will do in the following will be to try to understand the properties of this steady state and compare them with the patterns in real ecosystems. So beside this parameter, I have another freedom in this model, which is to choose who are the neighbors. So the simplest rule would be to just say that if an individual dies, the only individuals that can be copied there are the nearest neighbors. or I can have a more general kernel in which there is a probability that an individual at a given distance can disperse its seeds and occupy. I show you in this slide. So you can see that the nearest neighbor diffusion will give you these quite compact clusters of different species, where here different colors again are different species. Whereas if you have broader diffusion, you will have a more, say, mixed situation, where still you can see some patterns. I don't know if you can see some different shades of green in this figure, but again, these clusters are not compact, so species can penetrate each other. So essentially, this is the idea. So you have this model, you have these two different dispersal mechanisms, and what the program would be to compare the patterns generated by these kind of models to the pattern that one observes, say, in a tropical forest, as you can see in this photo. Okay, so now I have to enter into a slight technical detail, but I think maybe it's appropriate to this audience, otherwise statistical physicists will get bored. So there is one property of this model that is quite useful, both to understand its property analytically and also for simulation. And this property is so-called duality. So in statistical physics, we say that two models are dual when a configuration of a model can be mapped into a configuration of another model. In this case, duality goes as follows, and to keep things simple, I will consider the one-dimensional version of the model instead of the 2D because it's simpler to represent. So on the left, you see the same model I discussed so far, but in 1D, where the ecosystem is one line, and on the vertical axis, you see time. So in this say, simulation, in the first step, a new species, yellow, has been introduced on one side, and then green has reproduced and invaded one side of the red species, and then you had red that reproduced again, and so on and so forth. So this is a possible sequence of events in the water model in one dimension. So in the backward simulation, which is the dual model, I would represent final configuration of the water model as a set of random walkers. And at each step in time, so in this case, time goes in the opposite direction respect to the previous model. So if there has been a birth event in the forward model, I would have a movement of one of these random walkers in the backward model. So if you focus on the last two lines, so between the second last and the last line, in the left case, you had the reproduction of blue that invaded one slot of the red species. And in the backward simulation, I have a movement in the corresponding direction of the individual that would be the offspring in the forward model. Does that make sense? So to each birth event, I would associate a movement of a random walker from the daughter to the mother in the backward simulation. And since these events are random, this movement will correspond to random walk. So each individual parent can be either to its right or to its left with equal probabilities and with constant rate. So this could happen to all individuals. The other thing is that if two walkers fall on the same side, it means they have a parent in common, and so there is coalescence. So the two walkers will fuse and become one single walker, and this means that the two individuals the walkers come from are from the same species, because they have a parent in common, or an ancestor in common, if it's more than one slot in the past. Finally, birth of new species in the forward model will correspond to killing of random walker in the backward process. So this will correspond to this X in this figure. So when I draw with an X, it means like, for example, with this yellow species, that was appeared at some point in the past. And it will mean that I don't need to search anymore for the parent of that walker because that species was birthed at that time in the past, and tracing back all the walkers that coalescent to it, I know all the family tree of that species. So the nice thing of this trick is that you can see that going back in the past, I start having this empty slot, which means I can reconstruct this final configuration by simulating less and less particles, which means that for numerical simulation, this is far more efficient than simulating the forward model. The other interesting thing is that since we know a lot of things about property of first passage time around the walkers, this approach can also be used to estimate scaling properties of this system. Okay. So using this kind of simulations based on this coalescent approach, one can measure the species area flow predicted by the Boulder model. And you can see that quite nicely, even if the Boulder model is a very simplified model, it reproduces these three phases that are observed in real ecosystems. So in particular, you have this steep initial increase that is dictated by this dispersal kernel, so how far individual can disperse. And then you have this non-trivial sublinear growth of the expected number of species. And finally, growth becomes linear again for scales that are determined essentially by the rate of introduction of new species. So we have been working quite a lot in trying to understand what determines this exponent, because one has this idea that exponents tend to be universal things, and so we wanted to understand what is this number, what is the prediction of the neutral exponent. And this is related to, again, to this problem in statistical physics, which is, imagine that I have a lot of random walkers on the plane, and they can react with each other. So if they touch each other, they become one single random walker. So you can ask, if I have an initial density of this walker, this density will decay in time because of these coalescent events. And if I do a mean field analysis, I would expect that the decay would be like 1 over t. But of course, this does not need to be a mean field process, and therefore the decay can be different than 1 over t. And in particular, it has been studied that this decay depends on the dimension. So in 1D, the density will decay like 1 over square root of t. In 2D, there is a logarithmic decay. And in 3 dimension, also it decays like 1 over square root of t, but it will not decay to 0, so there will be a final density of walker. And this is related to the fact that 2 dimension, if you have experience with simple non-equilibrium critical phenomena, is the critical dimension for random walkers. So if you have 2 random walkers in 1 dimension, they will always meet eventually. In 2 dimensions as well, but 2 is the critical dimension, and above 2 dimensions, it is possible that 2 random walkers will never meet, so they will depart and never encounter each other. So this logarithmic behavior is typical in statistical physics of a critical phenomenon of the critical dimension. So this is something I would like to, this is one of the leitmotifs of this talk. So interestingly, 2D is the most interesting case for ecosystems because ecosystems now these 2-dimensional spaces, and it happens to be also the critical dimension. So the fact that it's a critical dimension has also other appears in other observables. So for example, this is a nice study by Richard Condit and co-workers, again based on tropical forest, and what they observed is the probability of finding 2 trees of the same species at a given distance. So this would be something related to a correlation function in statistical physics. And you can see that this, again, is predicted by the neutral model to decay like 1 over the logarithm of r, which is, again, is a signature of being critical. And you can see, again, you don't have many orders of magnitude, but there are quite clear evidences that the decay is logarithmic also for real ecosystems. Okay, so in the case of the Potter model, we can move into try to understand the behavior of this exponent. So first of all, the exponent does not change much if you change the dispersal range of the species, and in particular, you can scale these distributions on top of each other by changing the dispersal. So it seems like there is a simple transformation that, changing the dispersal just rescales the length scale from this problem. On the other hand, there is a dependence on this parameter, which is the speciation rate, by the rate of introduction of new species. In particular, if we make the rate of introduction of new species smaller and smaller, this exponent becomes more, this power law becomes more and more flat, so the exponent becomes smaller as well. So we analyzed this thing, and we found that, again, different models have that slightly different slope, but the behavior seems to be that the inverse of the exponent is proportional to the logarithm of the rate of introduction of new species. So this is, again, consistent with this logarithmic behavior that you will observe always at critical dimension. But we were curious whether one can really test this law, and the best thing we could found, since it's hard to estimate the speciation rate, is to say, well, speciation rates are related to lifetime. So imagine that the rate at which new species occur scales as a power of the lifespan of species. Then you will expect that the inverse exponent would also be proportional to the logarithm of the species lifespan. And this seems to work pretty well. So if I show you here the inverse of the power law exponent for different groups of species, plotted as a function of the logarithm of their lifespan, and they seem to fall on a straight line. So it seems like this prediction is consistent with, at least, there is some evidence that this prediction makes sense. So in the last few minutes of my talk, I would like to tell you about something which is a bit more of an open problem. And it's always related to this idea that we want to characterize the biodiversity by looking at scaling in the flavor of statistical physics, which is essentially how things change by changing the spatial scales. However, we have just seen that the models, the simplest models for this system are models that have 2 as their critical dimension, and 2D is the relevant dimension for most systems. So this means that we expect some kind of broken scaling variance. So this is something also that is not often stressed enough in statistical physics. If you have a system at the critical dimension, even if it's critical, you have logarithmic correction to the scaling laws. And this logarithmic correction means that the scaling laws are not real scaling laws, because logarithm is not a scaling variant function, which means if you change scale, you will not have a simple power law behavior, but you will have these corrections. And okay, but this is something about non-saturated environment. I think I'll skip that and just move to this last thing, which is, so if I look now at behavior of the species abundance distributions, which are again the number of species having a given population, the distribution of the number of species having a given population in a system. So what one can do is to take one of these big tropical forests, sample areas of different size, and try to rescale these curves on top of each other. So this would be the traditional approach in statistical physics. So if I have observation at different scales, I will try to rescale them and see what's the exponent like. This would be something called finite size scaling approach to a critical system. And what this study observed is that to obtain a good quality of collapse of these different curves, so these again are experimental data or observational data, you can't simply rescale trivially with the average number of species or the average population size, but you have to take into account some logarithmic correction. So here you can see that they are plotting, so this is the cumulative distribution, and it's multiplied by the logarithm of the average number of species, plus 1, plus correction parameters, time again the logarithm of the number of species, and similarly on the x-axis. So you can't simply rescale with the system size, but you have again these logarithmic corrections. And what we did in this review, just to verify that this is consistent with what we know about this model, was to do the same thing. So we simulated the water model, and we took sample of this configuration of different size, and we sampled in this way this species abundance distribution, which is again, in a given area, how many species you have with 1 individual, 2 individuals, 3 individuals, and so on. So you get, of course, that if you increase the sample area, these distributions get a longer and longer tail, because you have a higher probability of sampling very abundant species, because the sampled area is larger. But then you can try to rescale these curves on top of each other in different ways. So the simpler way would be what you can see in panel C, which is just rescaled by the average number of individuals, and you can see that the collapse is okay, but it's not perfect. And again, this is really based on an average over really many simulations, so you can read the differences are real, are not due to random fluctuations. And you can see that also in this case, if you include this logarithmic correction to scaling, you obtain a much better collapse. So this is again a signature that there is some need of this logarithmic correction, and this logarithmic correction might be observable in real ecosystems. So I move to my conclusion, about at the end of my time. So I hope I convince you that ecosystems are non-equilibrium. You can consider them as non-equilibrium systems characterized by some kind of scaling behavior with the space. And if you consider the simplest models for these systems, these are models that have 2D as their critical dimension, and as a consequence, you have these non-trivial logarithmic behaviors and corrections to scaling, which are things we are familiar with from statistical physics, and interestingly, these things can be observed in biodiversity data. So this is my conclusion. I thank you for your attention.
Interesting video talks, and is there any questions? Any questions from our students? Okay.
Thank you very much for a very interesting talk. Just a question about, you're showing the spatial neutral model, right? That can reproduce the species area law.
Yeah.
Do you have a theory for that? And we also see that 3 different regions showing for different power, 3 different exponents. So what would be the transition point or the transition ratio for the area? Do we have a theory for that too?
Yeah, let me go back to, yeah, I was a bit mixed on this part, and that's a good question. So, essentially, okay, so this random walk analogy helps understanding these 3 regions. So, the first region, essentially, these are individuals that are, so, K is the distance at which individuals can reproduce. So you can imagine that at a distance large smaller than K, or equivalent areas smaller than K squared, everything is well mixed. So you have a large increase of the number of species because these species can mix each other very easily. So let me go first to the last part, which is easier, and then I go to the difficult part. So the last part, so in this backward formulation, I kill random walkers at a rate nu. So, which means that because of diffusive scaling, there is a maximum area that these walkers can explore before being killed, which is 1/nu, scales with 1/nu. So this means that if the area is much larger than 1/nu, species are essentially independent.
Okay.
So essentially, the two walkers at a very large distance will not meet each other because they will be killed before that. Or in the forward model, you can think that essentially this speciation rate sets a maximum size for species. So there is a range in which there is a power law distribution of clusters, but at some point there is a cutoff because of this speciation rate. And this is also like in the mean field case. So this difference between the birth and the death rate creates an exponential cutoff at the end. So there is a maximum size. And beyond this maximum size, you are essentially seeing independent systems. So things grow linearly again. So the power law regime is a bit more tricky, and essentially the only way to understand it is by some kind of asymptotic matching. So we know the behavior at large scale, we know the behavior of small scale, and one can try to match the regime assuming that there is a scaling in the middle. So there is not really a theory, but it's more like, we know the endpoints, and we imagine that there is what is in between should be state-free, and therefore you can get estimates for this exponent. I admit it's not so satisfactory, and it would be nice to be able to solve this model, but unfortunately, to the best of my knowledge, nobody succeeded yet. So I think this is a very beautiful open problem for skills.
Okay, thank you.
Any questions? Okay, I have some follow-up question on this slide. So you mentioned about dispersal kernel. When you say dispersal, do you mean migration of individuals?
So in this case, it's like local dispersal. So we are thinking about groups, and simply this will be how far seeds are projected. So what you are thinking of, again, this figure perhaps illustrates it. So if a tree dies, the spot will be colonized by one of the neighbors, and it can be just really the next neighbors, or it can be few more neighbors. And again, this of course depends on the species. But normally in these models we introduce either a square or like a Gaussian kernel. So it will be a Gaussian function centered at the spot, and according to this function you will pick the parent that will colonize that spot. Does that make sense?
Yes, I'm just wondering how is it different from a discrete diffusion? So I'm asking is because in some ecological model, people would put in the migration rate for species, and in the calculation, in the mean field calculation, it can derive into a diffusion coefficient in the differential equation. Right, and we know the diffusion coefficient is very important for the tuning pattern formation. So I was wondering, yes. So
I think what I know is that in this case people often tend to distinguish between local dispersal and global dispersal. So you have essentially events in which, say, seeds are projected 10 meters or meters away, or you can have events where, for example, there is strong wind and seeds can end up even kilometers away from where they started. So there have been some generalization which people use kernels with uptails to try to mimic these long-range events. Or there are other models where you essentially consider that you can have individuals coming from outside the ecosystem. So there are there is really the system is open and you can do migration.
Right. So sorry.
So if you're asking more about if we know the shape of the kernel, I am not sure. Perhaps there are data. I'm not sure how good they are.
Yeah.
Because of course, yeah, I guess what you mean is that if the kernel has like a box shape, then that can cause pattern formation. Is that
Right. So that does that mean that if you have a long range dispersal, then the scaling role will be different, right? So you won't get the
Yeah.
same.
Yeah.
Yeah, that makes sense. Okay. I have no other questions. So at the beginning you mentioned that the stochastic patterns. So can you please explain again what is the role of stochasticity? What is your nodes?
I don't know. First of all, when I mentioned pattern, I wasn't. I was mostly thinking about these power law behaviors. So the behaviors of, for example, number of species and distributional number of species and so on. So I didn't. It was somehow in a broad sense, not in a specific sense in terms of pattern formation. So in these simple models, I don't know about pattern formation unless, as you say, you pick, you use a kernel which would form this pattern. But that would be, of course, possibility. The role of stochasticity. So in these cases, of course, stochasticity is really the main force for everything. So the fact that since all species are equivalent, the fact that a species becomes large or small, it's all due to fluctuations. So really there's no, since there is no difference among species, really it's all due to fluctuations. Again, people have been questioning whether this is true for real ecosystems, and I am pretty much agnostic on this point, but still it seems like somehow the universality class is right in the sense that these models at least seems to capture the exponent and the scaling behavior that you see in real ecosystems.
Okay, thank you. Is there any questions? If not, let's thank Simone again. Thank you. So,
Thanks.
thank you very much. See you later. So we're going to have a short break. So we're going to come back at let's come back at 10:15. Is that right? 10:15.